so we can okay, great. So we looked at we started looking at standard deviation yesterday. So let me, I think we looked at this. Let's just go where we reached. Okay, yes, we were here. So we were looking at how you can analyze and how you can quantify random error. So we looked at the fact that you're going to have two types of errors, okay? So there are those errors which we call the systematic or determinant errors. Those are errors which you can actually identify and actually remove from your analysis, right? But then there are those particular errors which we call random errors or indeterminate errors. Those ones you can't ever remove them from what? From any experiment that you are doing. So what scientists do is that that's why they use all those things like the mean, like the standard deviation, just to be able to be certain to a certain degree to say, you know what, the data which we've produced is actually some data that actually works, or rather not that it really works anyway, but it's data that we are sure that even though there is error, we can tell you that it's that the error is 0.02. Okay, then someone know, oh okay, so then this data is very reliable, okay, because the error is not too much. And that's why you would see maybe certain things where they say 2% plus or minus 0.2, isn't it? So they're just telling you that how we measured this to be this percentage, but it can either be 0.2 above or 0.2 what less. So all those is a way of quantifying the random error. So there are a number of terms that we have to appreciate, and this is short-term precision. So what occurs in this is that the analysis is run at the same time by the same analyst using the same instrument and same chemicals. So let me just explain this. So remember, we discussed what precision is. Huh? That precision is just how much in agreement the results that you've obtained are with one another. So, what this entails is that if I do an experiment and I've produced a value, then me, the same person, at that particular same time, using the same instruments and the same chemicals, I then repeat the experiment to see what values I'm going to get. Then what I'm trying to achieve there is short-term precision. It's called short-term because of course you could imagine it's done at around the same time, and this is the precision which you can, okay, you've done the experiment again, you run through. A best example is how you do your titrations in the lab. You have the one which you call the trial. Then you do the first run, second run, and the third run. What you are just trying to achieve there is for you to have some precision, and it usually be done by the same person using the same pipette, using the same burette, using the same beaker, using the same chemicals, but you are just trying to achieve a certain level of precision, right? So that one is going to be classified as a what? As a short-term precision. So that's about it. Then we now go to the long-term precision. So what happens for this long-term precision? That's where results are compiled over several months on a regular basis. So this is where maybe let's say you are trying to assess maybe how much copper is in the copper ores that are being produced, maybe let's say by Kansanshi, right? You're trying to analyze. So you maybe you'll be saying, okay, so in we are going to be analyzing it maybe per 6 months, right? So you go there in January, you assess, then you go there again in June, you assess again, you go there in January. So anyway, but it's you're trying to see really are the values that they are getting over a particular period of time, are they in agreement? That's going to tell you, oh, maybe the copper amounts in the ores Are they, is it that they are decreasing, or maybe it's the methods that they are using that are not doing them what justice. So all those things are going to come out in that long term precision. Then repeatability. So repeatability, you're just saying it's basically the short term precision under same operating conditions. So let me give an example. When you've done your experiment and you've done your back titration and you found maybe your concentration to be zero point 0.1 moles per liter. Okay, if someone repeats it at the same time, the same person, the same instruments, and the same chemicals under the same operating conditions, meaning the temperature hasn't changed, nothing has changed about the conditions. When you find that you get a value which is in agreement, what that entails is that your what that your values are what are like that sorry that your values are repeatable. Okay, they've got repeatability in them. Okay, so they've got repeatability in them, so they've got short-term precision, in short. Okay, so that's something important to take note of, huh? Okay, so that's repeatability. Then now reproducibility. Okay, so that's just coming from the word reproduce. So what reproducibility is all about is, this is where, let's say, we've done an experiment here in Lusaka on the copper ore. Then we get a replicate sample and we send it, let's say, to Kabwe, and we send another one to Northern Province. We send another one, let's say, to Muchinga, right? And then all the laboratories, after they've done their work, then we get similar results. That means that our results are what are reproducible. Okay, so that's about it. Then ruggedness. So ruggedness, it's simply the degree of reproducibility by one laboratory under different conditions. So what this means is, remember, for reproducibility, we are looking at what? At different laboratories, isn't it? So multiple laboratories, yeah, multiple laboratories to obtain same results. But for ruggedness, it's pretty much the same values, or rather, let's say the same chemistry lab. They assess. Okay, so they do the titration. Maybe they do the titration when it's very very hot, and then they do the titration when it's very very cold, and they do the titration when it's raining heavily. Okay, anyway, but not a titration, but they do any analysis under very different conditions. And then ruggedness is just telling you what's the degree of reproducibility, or what is the chance, or and to what degree are you going to get values which are close to one another, even under different conditions. And because you're using different conditions, meaning that it's not an experiment that you just do one after the other. It's going to take time for the conditions to change, right? And then for you to be able to repeat the experiment again. So that's why it's called long term precision, right? Long term precision. So that's about that. Then you've got robustness or reliability. So this is basically, is your accuracy and precision under small changes in condition reliable? Okay, let's say when you've done your experiment, let's say when it was let's say 24 degrees Celsius temperature. If the temperature changes by a small margin, are your values still accurate and precise? Okay, so that's reliability or robustness. Okay, and this is very very important, because it would be scary if, you did an experiment in the morning, and then you repeat the same experiment maybe in the afternoon, and then you get very, very different answers, then that would be very, very scary. Okay, so but if you get similar answers, close answers, then you know that your method, your analysis is robust or it's reliable. So now what happens is that we are going to get certain values. When we've done an experiment, we are going to get different values, and we are going to have what we call the confidence limit. Okay, so the confidence limits, these are very, very important because these are going to give us, let's say when they are telling us to say, if you don't have a mask, the chance of getting COVID is this percentage. So they are telling us that percentage because they are confident within a particular limit. Okay, so they've given us that percentage, and that percentage is part of a range, but that percentage that they've given us that percentage with a lot of confidence and a lot of surety. Okay, so the confidence limits, this simply refers to the extremes of the confidence interval. So if we say that the chances of getting COVID without a mask are maybe 89 to 90%, right? So those extremes of the confidence in either, if that's my confidence interval, then uh you could call those my confidence limits, meaning that I'm very certain that it's not below 89, it's not above 90, but it's just within this particular range. So, or this is the range of values within which there is a specified probability of finding the true mean, which is the mu, at a given confidence limit. So now what happens is that if I then give you that range of 89% to 90. This simply means that for that particular range, I know that even though it may not be accurate, but I know that within that range, that's where there is a specified probability of you being able to find the true value or the true mean, or that one which we call the true value, right? So why are they saying at a given confidence limit? Because or at a specified probability, because again it comes with probabilities, right? Has someone, or have you ever told someone something, and then like you tell them with so much confidence, say, you know what, what's happening around is this and that, and then they said, okay, how sure are you? And then you begin to stutter. Okay, so in short, what they're just asking from you is, what is your confidence limit? Tell me, what's the probability that what you've told me is actually true? So that's what they're just asking from you, right? And the confidence limit is an indicator of how close the sample mean lies to the population mean. So we discussed what the sample mean is yesterday and what the population mean is. So what this simply means is this, right? So we know that that U-shaped thing, we call it a mu, that's for this population mean, is equal to x, that's for the sample mean, but it should have dash on top, plus or minus. So what plus or that minus is giving us that again that I talked about, that uncertainty, okay? That plus or minus. So the confidence level is a good measure of also how close the sample mean is to the population mean. So these are things that we discussed to say if the z is 1, and anyway we looked at this with very wonderful diagrams yesterday. Perhaps you would remember. So remember, anyway, we looked at it. So what then happens is, for the confidence limit, okay, if we are looking at n measurements, so measurements simply means if we are looking at a particular number of measurements, let's say we are looking at, let's say we've, like for the example that we've been using for a long time now about the copper ore. If, for instance, we are trying to assess the amount of copper in the copper ore, okay, and then we've got 6 replicate samples. That means that our n is going to be 6, because that's the number of what? That's the number of measurements. So what that tells us is that the mu, or the population mean, uh is going to be equal to the sample mean here. So you see that dash that I was talking about on top, plus or minus the degree of what? That's the z1. The z1 is just giving us the degrees of how far away from the mean we are, and that's why you saw that for the previous one, it was actually z1, z2, and z3, right? And then we've got the sm, and don't worry, we'll talk about, we talked about the sm yesterday. Okay, we talked about it. So now, small letter s, we know it means for what's this? It means, it rather stands for standard deviation. Okay, so standard deviation is not a good estimate of variance. So that's variance there, isn't it? Okay, so it's not so it's not a good estimate of that. So since insufficient replicates are made. So what then you do to express your confidence limit is a test that you call the student's t-test. And I looked at your tutorial sheet. There were a number of questions which were very, very much based on these things, about the F test, the Q test, student's t-test. You have to know when they are used, because they'll give you variances, then ask you to compare them. So what test are you going to use? Because if you don't know the test you use to compare variances, then you can't answer the question, because there are a number of tests. There's the t test, there's the q test, there is the f test. So it's very, very important to understand, and that's why, like, from the beginning, I've been using as many examples, so that you can be able to grasp these things. So the student t-test is used to express the confidence limit. Okay, so the t-test is also used to compare results from different experiments. So in case you are studying, those are things you have to write. What are the functions of the t-test, or in which cases do we use the student t-test? So we use it when we want to express the what? The confidence limit, and then we also use it to what? To compare results from different experiments. So let's say I did an experiment and someone else did an experiment, and then maybe let's say I find my percentage to be 2.5, and someone else finds maybe 2.7. Then we are trying to compare our results, because you can't just say Steven's results are wrong or Steven's results are accurate. No, you need to have a test that's going to be unbiased in any or rather, which are not going to be biased in any particular form, so which are going to be unbiased. So that's why we could want to use a student's t-test. So what do you do? So you calculate your t. So like, how do you calculate your t? You do t, then you've got that value there. That would be for the sample or for the mean, depending on what you're analyzing. But since usually we use this with the mean, as you may have seen. So what you do there is you get the mean minus mu, which is the population mean, over standard deviation. Okay, so then that is going to be your t. So what this simply means is, if I come with an experiment and someone else comes with an experiment, what you do is, the from my values, I have to find the population mean, I have to find the sample mean, and I have to find the standard deviation. And for the other person's sample, the same things have to be done. Then we then have to calculate our t, just by substituting in that experiment, oh sorry, in that equation. Then uh okay, so then uh you may be wondering, how do we find the population mean? And that's a very good question, because you remember from what we did yesterday, we said that the population mean, it's usually for things where you are looking at an infinite number of measurements, right? So, and maybe you're only having maybe like seven measurements. How can you use something that is infinite? Like, how can you find a population mean for seven samples? So that's how you can use this particular equation to actually find the population mean. So what does this tell you? It tells you that if they want you to calculate the t, okay, the student the t value of the student's t-test, usually they will give you the samples, maybe there may be four, then they may give you the mu, okay, or the population mean, but the mean, they expect you to solve it, and we discussed how to solve it yesterday, and the standard deviation as well, that's something that you can solve. But some other times they can give you the t, which is the student t-test value. They can then give you the standard deviation, and they can give you the mean. And you've got the number of measurements, let's say seven. Then they ask you to calculate the what? The population mean. Okay? So uh that's the value there. Or that's the formula for calculating the population mean. Just in case you found yourself in a situation where they've not given you the they've not given you the population mean, but they've given you those other three things. So that is the range of confidence interval is. So what then they are telling you is, remember, we said that the confidence level, or the confidence limit, which is a range of the confidence interval, is it's actually gives us a way of comparing the what? The population mean and the sample mean. That's why we've got there the plus or minus t value times standard deviation over square root of what? Of the number of samples. So you can see that it can either be below the mean, that's when we say mean minus that, or it can be above when we say mean plus what? Plus ts over square root over number of samples. Of course, t meaning for the t-test value, and s meaning the standard deviation. So then, for better precision, you can reduce the confidence interval by what? By increasing the number of measurements. So what simply means is that, look at this, right? Look at this n. It simply means when you increase the denominator, okay? So if someone, let's say, is having an experiment with 10 samples, it means that, and then of course the t value may be constant, relatively constant, standard deviation again, excuse me, but it tells you that if you increase this number of measurements, then you are going to reduce the value of this ts over square root of n. And once this reduces, it means that the difference between the population mean and the sample mean is going to be low. Thereby, you are going to reduce the confidence interval, not the yeah, so you're reducing the what? The confidence interval, meaning that your values are more likely to have a good and better confidence level, isn't it? Because you've reduced the confidence interval. If, like, okay, let me try to put this into perspective. If someone asks you to say, or maybe you say no, this is what's going to happen tomorrow, then someone asks you, how sure are you? Then you say about 50 to 90%. That's how sure I am. And then someone tells you, I'm sure by 70 to 80%. Trust me, the one that has said 70 to 80%, you're going to believe the one that has said 70 to 80% better than someone that's saying 50 to 90%, even though they are going above 80, right? But again, it can either be 55, it can be 52. So you see that the confidence interval is so much, and so it casts a lot of doubt on the credibility, validity, and reliability of what? Of those particular results, right? So that's putting what is there in context. So then what happens is this. Uh, there are tables which are called the Ttest tables. I'll download them for you, and then I'll be able to send them to the Google Classroom. So basically, what happens is this. Let's try to look at an example so that we can see how we can. Okay, and we'll look. We'll use the notes, and then we'll draw up an example from there. So, uh, how then do you begin to use this student t-test? So there's what we call the pooled standard deviation. Okay, the pooled standard deviation. So this is a weighted average of standard deviation for two or more groups. So remember, again, remember here we are just comparing, right? Like remember, like I said, like let's say I did an experiment and someone else did an experiment. Now we are trying to assess which of the two experiments are, you know, so which of the two experiments are more accurate. Okay, so now that's something that's very, very important to take note of. So then we are trying to understand this to say which of these tests is more accurate, or rather which of these values are what are more accurate. So what then you're going to use is you're going to use the pooled standard deviation, where you're trying to find an average of the standard deviations for those samples that you are trying to analyze. Okay, so that's that. Then for the calculate the t, we've looked at how to calculate the t. Then comparing the calculated t to the value of t from the table. So uh perhaps you saw me asking for a what's this? Asking for a tutorial sheet in your group. So we'll definitely look at an example on this. But I just want us to understand, and then so that when we even when we will be doing the the calculations, people will understand what we'll be doing, because these questions I saw them in your tutorial sheets, they are there. So for those that were not sure if this is in your syllabus, you can look at the tutorial sheet again. So yeah, so you calculate the pooled standard deviation, but usually for really, but wait, which chemistry is for medicine? 10 is for engineering. Oh, okay. But again, you know that what's this? You know that the like how do I explain this? You know that this topic is very, very medical. I don't know really like how your schedule is, but this topic is very, very medical. At least that's what I would say. Also, you're saying that no, but the tutorial sheet that someone sent me is for chemistry 1000, and it's April 2021. No, but wait, but didn't okay, but didn't someone say that you were told to study it? Who's okay? Okay, so who is that one that said that you had to study it? Yes, you were told by the lecturer. Yeah, exactly. Because yeah, exactly. Because the tutorial sheet that I'm looking at is April 2021, and it says Chemistry 1000 Introductory Chemistry for Medical and Health Sciences, Tutorial Sheet 4, Sampling and Treatment of Analytical Data. Yes, it's there. Just try to check your course outline properly. It's there. It's there. Yeah. It's there. Okay, so we looked at the okay, so you calculate the pool standard deviation, you calculate t, and then you compare the calculated t to the value of t from the table. So remember, I made mention that these f test, q test, t test, they've got different tables. So basically, what happens is this. Let me just try. Okay, maybe let me see if there's something that would have. Okay. Okay, let's first look at the formulae, then I'll explain, or maybe let me explain, then we'll go to the formulae. So, what you do is you calculate the pooled standard deviation, which is just an average, okay, of the standard deviation for the samples that you are trying to add, for the samples that you are trying to analyze. Okay, so for those samples that you are trying to analyze, you find an average, right? And remember, you don't just add standard deviations, because like we said yesterday, standard deviation is not additive, so you don't just simply add it. That's why there is this formula that I'm going to show you. Hope we've gotten that point. Then you calculate the t-test value. Now, there is what we call a t-test table. So what a t-test table does that it's got different values, and these values are going to be tabulated at different confidence levels. So there is 90% confidence level, 85 confidence level, 80% confidence level, 95 confidence level. So what happens is, usually in medicine and in statistics, you always want to go for 95% confidence level, isn't it? Because you need to be very confident that the drug that you want to start giving people works, isn't it? So we usually go for 95% confidence level. So what then happens that when we've calculated the t, then we are going to go now to the t-test table and see, just follow me, and see how the t value that we've calculated compares with the t value that is at 95% confidence level, okay, in that thing. And if the value that we get, if the t value that we calculated is greater than the one that is tabulated on the t-test table, then the two results are significantly different. In other ways, that casts a lot of doubt on the strategy, or rather, on the validity, or rather, on the reliability of the results that you've gotten. So if the calculated t value is greater than the one that is tabulated in the t-test table at 95, but of course, some questions will tell you 85% confidence level. So always pay attention to what confidence level, because you get the confidence, because you don't read the question properly. You use 95% confidence level, and the question is saying 85% confidence level. You get the question wrong. Okay, so that's about it. So yeah, so you calculate your t value, then you compare it with the tabulated value at what, at 95 confidence level. Okay, at 95% confidence level, then if the value that you've calculated is greater than the value which is tabulated, this tells you that the two results are significantly different. So now let's now look at this example, although it's not really an example per se, but let's now narrow the things that we've done. Okay, so imagine we've got two measurements, right? Let's say I did the measurements and then someone else did the measurements. So we've got n, which is the number of set of certain measurements, and another n, the other measurement that someone did. And both of these measurements, they're going to have their averages, okay? They're going to have their sample means, isn't it? Those are the ones you are seeing, X with a cat thing on top. That stands for average, or sample mean, isn't it? Then we looked at the equations, or yeah, on how you can find standard deviation. So for these values, you find their sample mean or their averages, you find the standard deviations. Then remember, we said pooled standard deviation is an average of the standard deviations. But remember, standard deviation is not additive. So meaning you can't just add, you get the standard deviation and you add it. No, you don't do that. So you use this formula. This looks complex, but let me break it down. What you are just doing is you get the standard deviation for the first sample, you square it, then open bracket, the number of measurements. Let's say we're looking at maybe six samples, you write six there minus one, okay, plus, then you square the second standard deviation for the second group of measurements. Then, if those are 6 or 7 as well, you write the number they are, then minus 1. Then, put a large square root, then over, you get the number of the samples of the first group and the second, then minus 2. And from what we discussed yesterday, you would remember that the square of standard deviation is variance. Huh? Okay, so we discussed that. So then, once you've gotten your pooled standard deviation, what then you do is you get a difference of of the sample mean of the first data set and the second data set, and that's absolute. So meaning whether that is first or that is second, when you subtract, whether it's negative or positive, the difference is going to be the same. And the fact that you're putting absolute meaning that it's going to end up positive either way, because you don't want to have a negative number here. So we are just putting it 1 and 2, just for it to look a little bit, what can I say, orderly. So that's about it. So now to find the t, so we've got that. Then over that, put standard deviation. Don't worry, we will look at examples. Huh? So then square root, multiply the numbers of the sample size over the, okay, so square root product of the sample sizes over sum of the sample sizes. Then we talked about degrees of freedom, right? So degrees of freedom, we know that for standard deviation, it's just simply n minus 1, because we're just looking at one uh, 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 data set, isn't it? But for this one, because you are looking at two data sets, but you can even look at more data sets, but because you're looking at two data sets, we're having number of samples in the first data set, that's plus the number of samples in the second data set minus what, minus 2. So that's the degrees of freedom. And in the t-test, that's what you're going to be looking at. There is anyway, I'll show you the table, or I'll send it to Google Drive. So sorry, to Google Classroom. So the degrees of freedom, those are some of the things which the student t-test table has. Okay, so you've used that, and also the confidence level that you want your uh, for which you are assessing your t value. Okay, so basically, okay, let's see. Okay, so basically, after you've done that, let's see. Yeah, so after you've gotten your t value from here, then you now go to the table. look at the degrees of freedom, and then look at your confidence level, and then see what t value is there. If it's greater than what you've calculated, then the population mean and the sample mean are not very different from one another. If what you've calculated is greater than what is tabulated, then they are significantly different. Okay, so that's that. Don't worry, look at an example. So yeah, then the other thing, you can also use the t-test to, or using the t-test for systematic error. So so remember, first of all, we used it to compare the means. So you can use it to compare the means. That's what we are doing. Then now, secondly, now to test for systematic error. So we know systematic error is something that you can do something about, isn't it? So systematic error is something that you can do something about. So if you can do something about it, it's something that you can discover. That's something that you can identify. It's different from random error where you can't completely rule out, or rather you can't complete, in fact you can't get rid or avoid or correct a random error because you don't even know where it's coming from and everything. So that's the key thing. But using the t-test, you can actually assess and check for systematic error, so that if the systematic error is there, you can figure out, check, investigate where it's coming from, and with that information, you can be able to look at what you are dealing with, and then say, okay, so probably let's do this and that. That way we are going to get rid of the systematic error, because systematic. Okay, so that's about it. So the new method is used to determine mean and standard deviation. So how you are going to do this is, you are going to find, let's say you are looking at a data set. Let's say, like the example we always look at, the copper ore. So I get six samples of my from of six replicate samples. We talked about what a replicate sample is. So I get six replicate samples, and then I find my mean. I find my mu, or my population mean. Then n there is just the number of samples. Then I find my standard deviation. I can calculate my t value. Now, for that t value, if then I say I want to analyze this, I want to check if this procedure is, or rather doesn't have a systematic error for a confidence level of 95%. Meaning that when I go on that t-test table, I'll be focusing on what? I'll be focusing on 95% confidence level. And then if the value that I've calculated, if the t value that I've calculated is greater than the one that is tabulated on the t-test table, it means that the new method, or the method that I'm trying to assess, that it's got a systematic error. Therefore, I have to identify where it's coming from and then get rid of it. So that's why all these things like titration and all these things, they've undergone through this thorough process, and now they can widely be used by students because people are comfortable with them, because they know the because they know to say, this is something that really works. So are there any questions up to this point? Okay, so if there are no questions, let's proceed. So yeah, so that's how we can use the student t-test for those two things. Then we now go to the f-test. So remember, know what these tests are for. So what is the f-test for? So the f-test is for comparing two methods, of course. So let's say we've got one method and then you're trying to determine if the two methods are statistically different in terms of precision. So someone comes up with a method and say, you know what, this method is very effective, and someone again says, no, this method is more effective than your method, and you don't want to be biased. You want to figure out which method is truly more precise, or even more important, you are trying to assess to say, even though these people are claiming that their methods are better, are they really different? Okay, so that's a question that you're asking. Are they really different? Which one should we prefer? Or maybe perhaps we can use either. And the answers which we are going to get are still going to be statistically correct. So that's what you are asking there. Now, what you use for this, you use variances. So we know variance is simply what? Square root of what? Of standard deviation. So what you do there, you see the f function is the ratio of the variances of the two sets of what? Two sets of numbers. So what is a ratio? We know ratio by definition is a fraction, isn't it? So what you do is, yeah, you get the variance, and you get the variance by squaring uh yeah, by squaring standard deviation. Huh? We discussed that yesterday. So now, one thing that is very, very important to take note of is that the ratio should be greater to 1. Now, what does that mean? And that's where many people make a mistake. The ratio, that f value, should be greater than 1. So, how do you ensure that your ratio is greater than 1? It means when you are given, and this question is in your tutorial sheet, that's if I'm not mistaken. Yeah, because I looked at it today. Anyway, but what this simply means is, because the ratio has to be greater than 1, it means that when you are given your variances or your standard deviation, so if it's a standard deviation you are given, you square it. If you are given variance, then you just look at it the way it is. But what should be your numerator? If the ratio is to be greater than 1, it simply entails that your numerator should be greater than your denominator. So if someone, let's say you've got the so for instance, can someone answer this? If you've got a variance of 2.5 and a variance of 3.5, which of these two variances should be the numerator? I'm sure you are saying 3.5, right? Because when we put 3.5 as the numerator and 2.5 as the denominator, then we are going to have a value which is going to be greater than 1. Then we can do our f test. Huh? So that's a very, very important point, because people will do it the other way around, and they find that the value of f that they found is not on the f test table, and it becomes catastrophic. So F values are found in tables, make use of 2 degrees of freedom. So meaning that the degrees of freedom you are using, so there are going to be 2 degrees of freedom there. And of course, those degrees of freedom refers to the methods that you are looking at, and then also yeah, so those F test tables are there. So now, how you do it again, it's the same thing that we've always been doing. So we found our f value. So if the value that we've calculated as our f value, if it's greater than the value of f at that particular f test table value that we are looking at, based on our degrees of freedom, okay, then we say there is a significant difference between the two methods. But if the value that we calculate, our f value that we've calculated, is less than the tabulated value, than the value that is uh, in the than the value that is in the table, in the f-test table, then we know that there is no significant difference between the two methods. And so whether you use method 1 or method 2, the values that you get are pretty much the same. There's no significant difference. Of course, there may be small differences, but it's not significant. So the word significant is very important. So how they'll ask you the questions was they'll give you samples and then ask you to say, are these methods, so this one was found from this from this experiment, and this one was found from this experiment. Are these val- are these values significantly different from one another? So that's pretty much how they would bring your questions. So there is a question. Yeah. So there is this method. Oh, sorry. This the question 11 in your tutorial sheet. It says a new method of determining cobalt in soil sample gives 99.35 percentage recovery. The variance is 0.185. The standard method gave 99.53% recovery. Variance is 0.152. In each case, three replicate measurements were made. Okay? Test whether the two means differ significantly at the 95% confidence level. So there, what are you going to be comparing? You're comparing two variances. So because you are comparing two variances, which test are you going to use? The F test. So yeah, and that's your tutorial sheet released in April. So yeah, these are very good questions. But anyway, so it's very very important you know which test you're going to use, because they'll give you all the what's this. They'll give you all the tables. So you can't say no. I'll just use the F table because it's the one I've been given. They'll give you the Q test table, the F test table, the T test table. So you have to know uh, how these tables are used. So we now go to rejection of results. So when you are doing an experiment, there are going to be those values which we call the outliers. Okay, so the outlier, this is a replicated result. So let's say you've got 6 samples, then 5 samples are close together, then the sixth one is just way overboard. Huh? So it can either be, it's very far from the other results, so it can either be the highest or the lowest value. So it will just be all over the place. So now this is called an outlier. Now, you don't just discard it. You have to justify why you are discarding an outlier. Yes, it's an outlier, but you don't just discard it. There is a protocol. Okay, and this is where we now talk about rejection of results. Okay, so there should be a justification for discarding the outlier. And what is that justification? Is that the outlier is rejected if it's greater than, okay, plus or minus 4 times the standard deviation. Okay, so what basically, okay, so meaning, or rather, yeah, if it's that from the mean, so it simply means if the value that you've gotten, you've done your analysis and you figure out that it's plus or minus greater, or it's greater than plus or minus 4 times away from the mean, or with a 4 times the standard deviation away from the mean, because know that that's the z value, huh? from what we are looking at a short while ago. So that's the Z value away from the mean. If you find that your outlier has got that, then you can reject it. Okay? And once you've labeled something as an outlier, then you don't use it in calculating the mean and standard deviation, because then you figure out to say, you know what, this was maybe as a result of a huge mistake. Okay, so this is very important, because how they would ask you is they'll give you samples, right? Maybe let's say 5 samples, and there will be one value which will be away from the others. Then they would say A, uh, find the mean, B, find the standard deviation. Once you know that it's way different from the others, some questions may ask you to find the outlier, some questions will not ask you. So you see someone just adding all of them and saying the test was easy. But how can you have 5.1, 5.2, 5, 5.6, and then you just have 15.5, and then you want to add them and find the mean? No, 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 that's an outlier. How can the others be in the 5 point something and it's gone to 15? So then that's how you see an outlier. Or it can either be the smallest, so maybe everything else is in 5 point something, it's in maybe 2 point something, or 1 point something, or 0 point something, then that's an outlier, because the difference is just too much, right? So those are some of the tricks. So some lecturers may actually say, determine whether that's an outlier or not. Others will just tell you calculate the mean, and everyone will calculate the mean and say, oh, the test was easy, the test was easy. And when they see the results, it's not something that they were expecting. So a new Okay, so that's about it. So, if then you figure out that that outlier is less than plus or minus 4 times standard deviation, then you can include the what's this. Then you can include the outlier in calculating your mean, even if it looks very far away from your other values. That's why we do the test called the Q test. Okay, that's why we do the Q test. So, are there any